Okay, Archimedes had to do all his calculations by hand. In fact, he didn't even have a slide rule because those were, in his time, far in the future. We get to use MATLAB, which is way better. Pi is already programmed into MATLAB to 15 decimal places, so 15 places after the decimal point. And that's good enough for what we need. Since it's so easy to evaluate in MATLAB, let's use Archimedes' method, but let's do this for a variety of ends or a range of ends, and let's make a convergence plot. So to start, let me say n equals 6. We'll start there in steps of 10 maybe, and let's go to, I don't know, 600. All right, we'll call P1 right there. You know, we've got to have this dots in here because we're working with vectors. N is a vector. You can see the first time I did this, I used lowercase n. I'm using capital N now to keep it consistent with the board. So there's that. And for P2, that'll be the circumscribed polygon. There it is. Okay, so we've got a vector of P1s and P2s. Yeah, let's plot those, I guess. So plot n, P1, let's make that maybe a blue circle, and n and P2, and let's make that a red diamond. And let's turn the grid on. Well, you can see that for low values of n, I'm pretty far off, and it gets closer as n goes up. Unsurprising there. But it's hard to get a real feel for how close we are. Well, since we already have a precise value of pi programmed into MATLAB, let's make a normalized error function. That'll be a lot easier to look at. Let's get rid of that. We'll call it ERR1. And I use the absolute value of pi. Now, pi in MATLAB, that's just the value of pi that's programmed in. Hang on, I'm going to need another set of parentheses here. There we go. Divided by pi. I don't need to see that. So that's the absolute value of the difference between pi and my estimate divided by pi. So that should be some really tiny number, ideally 10 to the minus bazillionth, I guess. So there's for the inscribed polygon. And let's just make another one for the circumscribed polygon. There, got that. Now, let's plot n, ERR1, and again, we'll use a blue circle for the first one, and a red diamond again. And let's turn the grid on. Well, I guess that's okay. It doesn't look better, does it? Well, here's what's going on. We need a way of making a plot that shows large numbers, or relatively large numbers, and relatively small numbers on the same axis. So this linear axis, that's not making it. Let's try something else. Let's recall that command, but instead of saying plot, let's say semi-log y. Okay, that's MATLAB lingo for let's make a log linear plot where the log axis is y and the linear axis is x. So it's semi-log plot. Ah, okay, now we're getting somewhere. Now, on this log scale, we can watch the errors get smaller and smaller and smaller. This is called a convergence plot. Well, this is a type of convergence plot. This is what showing the error, which hopefully will go to nearly zero. And during Archimedes' lifetime, he got about that far. So he got 4 or 5 decimal places of pi. Now, one thing I mentioned is that the inscribed polygon underestimates pi, and the circumscribed polygon overestimates pi. Well, what happens if I just take the average of the two of them? And let's just skip to the end. What if I say I want the last value of P1 plus the last value of P2. And that's what n does. It just gives you the last element of a vector. And the nice part about this is you don't have to know how long the vector is. And just divide that by 2. Okay. 3.1415999. Okay, that's not right, but it's closer. Well, is it? Let's do this. Okay, we've got a number now. It's 2 times 10 to the minus 6. Let's pull that plot back up. The 2 times 10 to the minus 6 is down here. That's 1 times 10 to the minus 6. That's 2 times 10 to the minus 6. So that one, the error is way down here. This is good. That means if I just take a simple-minded approach and just average the two values, the upper and lower bound, just blindly grab the one in the middle, I get a much better estimate. So let's review why Archimedes' method is such a good algorithm to learn from. It's easy to describe. It's not terribly hard to implement. It converges to the right answer. And perhaps most importantly, it gives us a clear estimate of the error. We know that we have an upper and a lower bound, and we know that the correct value of pi lives between those. So that's pretty handy. But there's one problem that's an absolute deal breaker, and that's that it takes forever to converge. If we look right here, if each one of these decades here is a decimal place, we're getting a decimal place. Out here, we're getting a decimal place every few hundred additional boxes, and that line is leveling out. If we get farther out, we're going to need thousands and thousands more boxes in order to get more decimal places. Well, you're absolutely never going to get a lot of decimal places this way. It's just too inefficient. So even though this is a good start, it's not a good place to end. We're going to need something better than this. Fortunately, we have all the tools we need to take the next step, and we'll do that on the board.